Okay, so more technical issues because why not? Working from home. I don't know why, but my printer decided not to print some of the text on these slides, so I had to write them in. I had to write them in myself. So, looking at now some other topics with the spin-spin splitting with alkenes. We've already talked about how hydrogens on a carbon may or may not be equivalent. So you can have an enantiotopic carbons or diastereotopic, hydrogens, not carbons. So if these two are on the same, if we have two hydrogens on the same carbon, they're twins, they're geminal. So what would make them this different is the way they have this right now. It looks like they're both two maybe methyl groups, but if we were to change this maybe to, I don't know, a chlorine and a methyl group, now these guys would be different. This would be two different sets, and what that means is hydrogen A is going to split the signal of hydrogen B and vice versa. So C, this carbon is not attached to any other carbon, so there's nothing on this carbon that's going to split these signals. A is only going to be split by B, B is only going to be split by A. So we would get two doublets. Let's say call this HA, and we get another doublet here, HB. And what they're saying is the coupling constant, the difference between these two peaks, is 0 to 3. So it's very, very small, very close together, 0 to 3 hertz. But we know they're coupled because they would have this. They would have the same coupling constant, J. Now, if they were cis to one another, again, we can also make this maybe isomer of what we were dealing with. Actually, yeah, it would be an isomer. It just wouldn't be a stereoisomer. A and B are only going to be split by each other, not by any other hydrogens on these carbons. So again, we'll get splitting. We'll get a doublet from A and B, but the coupling constant will be bigger, 5 to 10. So you could, I don't know, maybe look at a little bit bigger. I'll try to make it about the same. So 5 to 10 hertz for this coupling constant, and a large coupling. Large splitting or coupling constant when they're trans. So trans, they're further apart, a larger coupling constant. Cis, they're still not on the same carbon, but they're on opposite carbons, but they're on the same side, so it's a little bit smaller. And then when they're on the same carbon, it's very small coupling constant. So this is what we see here. We have E3-chloropropanoic acid. Hydrogens A and B are trans, so we see the difference here is the same, and A is on a carbon that has electron withdrawing group. You know, we call that Z in that chemical shift table earlier. So it's downfield from B. B is, you know, it's going to be downfield somewhat because of the alkene here, but A is HA is attached to a carbon that has this electron withdrawing chlorine, so it's downfield. But the main thing to recognize here is they're trans to one another. They have a coupling constant that's fairly wide, 14, and of course we know they're coupled because they have the same coupling constant. If it's cis, so these are isomers, E and Z. Here they're on the same side, and now the coupling constant is much smaller, so 5 to 10. So their cis is 5 to 10 for trans, or E in this. I should have put Z there because it makes it. I'm not saying Zusammen, I'm saying it's some kind of electron withdrawing group. So when they're trans to each other, it's 11 to 18. Okay, so here we have the spectra for vinyl acetate. So well, they've identified the various hydrogens. CH3 here, this HA, is a singlet, and it's shifted. It's not shifted downfield a whole lot. I mean, if it was just an alkene, alkane would be 0.5 to 1.5. So it's shifted down a little bit because of this carbonyl. But these guys are shifted well downfield because of these. Now, also note here, D is shifted downfield because of the alkene, but it's also on a carbon that's directly attached to an oxygen, and so it's shifted the most. And again, these are not a quartet. Remember, a quartet has this 1, 2, 2, 1 kind of pattern. That's not what you see here, or here, or here. These are doublets of doublets. So looking at HB, HB is going to be split by C into a doublet, and it's going to be split, so this carbon here, we look to the next carbon, it has one hydrogen, it's going to be split by D as well. So it's going to be split by a doublet here and a doublet here. We get a doublet of doublets. Same thing for, actually that was D. For B here, a doublet of doublets. So for C, we also have a doublet of doublets. Now notice this doublet and this doublet, the coupling constant is very small. Okay, that's because this here we're talking about the geminal splitting. Okay, BC. This is the BC splitting. This here's the BC splitting. You see the same thing here. BC splitting, or maybe in this case the CB splitting. Okay, this wider range here is from D. So just looking at B now, B is trans to D, so it has a larger difference between these two peaks. So a larger, this is the trans splitting. BD. Here C and D are on the same side, so it's closer. Right, it's closer than these two. This is the cis splitting. And that is what C and D. It's difficult to make out what's going on here with D, but it is split into a doublet of doublets. So here, I wouldn't have been able to tell you this without them. So if you imagine this is the center of mass of this signal, okay, it's split into a doublet of doublets. So we have the first doublet here would be BD, and that's the trans-splitting, so it's wider. And then that doublet itself is split into a doublet as well from C, so that's the geminal. And they've really expanded I'm sorry, that is not the geminal, that is the cis splitting. Okay, so here's the cis splitting C and D. I've already talked about the signals for B and C. Okay, matching the signals to the hydrogens for this compound. Notice the close geminal splitting we have here. So the geminals, this is one signal, this is the other. One is for C, one is for B. How are you going to tell the difference? Well, notice the splitting here. Okay, the coupling constant here versus here. Okay, the larger coupling constant here, 18, is for AC, or CA if you want. So this is the trans splitting. Coupling constant here is 11.8. We'll call it 12. This is the cis splitting. So that's BA. I'm sorry, here's BA. BA splitting, and this was the AC splitting. The close geminal splitting we see here is from C and B. C and B. And for this signal, this will be, well, if you wish, this is the signal. Let's do it this way. This is C, This is for hydrogen B. So this would be the BC splitting, if you wish, BC splitting. And what you see here is for hydrogen A. There is no geminal splitting, none of this really close stuff. And it's difficult to tell in this. I wouldn't attempt to ascribe the splitting to these, but we can definitely see that these two are the same. So it's responsible. Whatever splitting this is from the same carbon, or sorry, from the same hydrogen. So NMR of alcohols. Alcohols are kind of interesting. Let me redraw this structure. It's just plain old ethanol. Okay. So we have 3 signals. We have 3 hydrogens here that are going to be split into a triplet from these 2 hydrogens. So we see a triplet here? Yeah, that's for this upfield. So that's HA. We see a doublet, or 2 hydrogens here that's going to be split into a quartet. But then also, what about this hydrogen? Shouldn't it be a quartet plus 1? Shouldn't it be a quintet? Well, no, and there's a couple things going on here. First off, alcoholic hydrogens exchange in solution. So yes, they're weak acids. Ionizes comes off like an acid comes back on. So for that reason, and hydrogen bonding, they do not split the signal from hydrogens on adjacent carbons. Also, they are not split by hydrogens on adjacent carbons. I'll just say by neighboring protons. Okay, so what this means is for alcohols, this alcoholic hydrogen here, they're always going to be a singlet. So that's really easy to pick out. That's right here. This is the alcoholic hydrogen. Again, we have the 3 hydrogens here that are going to split into a triplet by these guys. So that's A, and then the 2 hydrogens here not split by this alcoholic hydrogen, only these 3, so we're going to do a quartet. Now for cycloalkanes. So if it was just plain old cyclohexane, you'd only have 1 signal and it wouldn't be split. Only 1 set of hydrogens. And if you thought of it, you know, kind of looking at it edge on, you have hydrogens on the top and hydrogens on the bottom, and aren't they different? Not if it's unsubstituted. Okay, so for it's just plain old cyclohexane, it's a trivial example. But as soon as you substitute them on, they give a complex spectra. The ring protons, let's just protons attached to the cyclohexane ring. If they're an sp3 hybridized carbons, they're going to absorb you get a complex splitting pattern, 1 to 2 parts per million. So well upfield. Now, an example here. Methyl cyclohexane. Let me just redraw this. Right. We'll put all the hydrogens in, but methyl cyclohexane, right? So here's the methyl group. I'm calling it F. F down here, well upfield. So this is these guys should be split into a doublet. You can't really resolve that here, but this is well upfield. The rest of the hydrogens in the ring here give you this smush here again between 1 to 2 parts per million. So it's a relatively simple compound, but it's really impossible to kind of decipher this. So this is where a computer comes in handy to match this with what they have in the known library. So if you did have something like this, you know, oh geez, I don't know what's going on here. What do you do? Well, there's something called carbon-13 NMR, and we will get to this in the next video. But essentially, in carbon-13 NMR, you're not looking at not looking at hydrogens and all the individual or unique sets of hydrogens. You're looking at all the unique carbons. And so, for methylcyclohexane, same compound we looked at before, it has a much simpler pattern. No splitting, by the way, in carbon-13. And there's these. Okay, carbon-2 is unique. Carbon-3 is different from carbon-2, carbon-4, and carbon-5. So you're going to get 5 signals. 4 and 5 are kind of right on top of each other, but it's a lot simpler and easier to decipher than this mess here. Right, so that was looking at cyclohexane. Right? Now we're looking at benzene. And again, if it was benzene, you just have all 6 hydrogens would be equivalent. You just get 1 signal. Trivial example, no fun. But if you put a substituent on there, so Z here again is a substituent, you get a complex pattern as well. You don't need to decipher this, figure out what's exactly going on. What you should recognize, however, is the ring protons on a benzene. Okay, they're going to be in this range of 6.5 to 8. Okay, so do we have anything below? This would be 6.5, maybe. The nature of this ring, whether it's of this substituent, whether it's electron withdrawing or electron donating, affects the shift of these ring protons. But again, don't feel like you have to decipher that. If you see a kind of a mess out here between 6.5 and 8, it's almost invariably a benzene ring. Alright, so we have this compound. Let's try to match the peaks to the protons here. We see a smush out here. This is between 7 and 8. So this is the ring protons. So I just put here the benzene ring. We have a nice quartet, right? It's not a doublet of doublets. It's a quartet. 1, 2, 2, 1. So we don't have any integration data, but what this tells us is that the hydrogen responsible for this is next to a CH3. Okay, so that's going to be these guys here. We'll call this A. I'm sorry. This is A. Call this A. This is B. B is next to a carbon with 1 hydrogen, but it's also got this. I don't know if you can see this. This printing again didn't come out too clearly. This is the alcohol. Okay, so B is next to a carbon which has a hydrogen that's going to split these 3 into a doublet. That's what we see here. So this is HB, and again, it's well upfield. Okay. HA here, this hydrogen is going to be downfield for 2 reasons. One is directly attached to an oxygen, and it's also next to this benzene ring. So that benzylic is going to shift it downfield as well. Okay. So that was HA. This is to HB. These guys here, the doublet from this hydrogen. This is also attached to the alcohol group. This hydrogen is the OH giving you the singlet. And don't try to interpret the protons on the benzene ring. Okay, to close out this lecture then, we have a compound C3H8O. We have a broad IR absorption from 3600 to 3200. What that's telling you is you have an alcohol. And even if you didn't have an alcohol, well, I suppose there's another possibility. But again, always look at the chemical formula, C3H8. Well, if it was an alkane, it would be C3H8. It's saturated. Okay, so there's no double bonds, no triple bonds. We don't have an IR absorption at 1700 indicating carbonyl. It could still be a, what do you call it, an ether. CH3, CH3, CH2. Okay. But if it was an ether, the splitting pattern would be different. We would get a singlet from this carbon. Oh, and by the way, they have also given us the integration data. We get a singlet from this carbon. We have a singlet here, but it's only responsible for one hydrogen. Here we would have three. So it can't be that. Instead, we have an alcohol. So the possible alcohols, we could either have one propanol or two propanol. If it's two propanol, actually it can't be one propanol, because if it was, we'd have 1, 2, 3, 4 signals. So right away that tells you we only have 3 signals. It can't be one propanol. Therefore, it's got to be two propanol. We have the singlet from the alcohol. We have 6 hydrogens, each split into a doublet. I should say there's going to be one signal from these 6 hydrogens split into a doublet. That's these guys. So it's a CH3, CH3. And then this bugger is going to be split into 3 plus 3 is 6. This should be a sextet. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7. Oh yeah, going to be split into a septet. 6 plus is the n is 6. 6 plus 1 is 7. So 1, 2, 3, 4, 5, 6, 7. Right. So this is the septet.